Hello everyone, in this video I'm going to be looking at the three different current potential difference graphs that you learn about in AQA physics at Key Stage 4, and we'll look at resistance, how that relates to current potential difference, and a few special types of resistor. Now the reason this video came about is because I had a few comments from students that I teach saying that this topic they were a little bit unsure about, which bits they needed to learn, which they didn't. So this one's quite just a comprehensive video on the actual bits that usually get examined. So let's think about how these three things, current, potential difference and resistance, all relate to one another. Now the resistance of a component can be found by measuring the current through and the potential difference across that component. So we're going to use one particular equation. Now the equation that we're going to use is this one. V is equal to I times R. Now you can rearrange that particular equation if you wanted the other individual components of that. So if you wanted I, that would become V over R. And if you wanted R, that would become V divided by I. Now let's put some context onto these letters. V is the potential difference. So V is what we describe as potential difference. So you might call it voltage. And so this one is measured in volts. The I is the symbol that represents the current or the flow of electricity, the flow of electrons more specifically. So the I is our current, and you might recall that that one is measured in amps. We'll put a little A for that. And R is our resistance. Now resistance, when we say that, essentially we mean resistance to the flow of electricity. And that has the unit of ohms. So we'll put in there resistance in ohms. And I'll put the symbol, you might see that particular symbol there for resistance. So that's the equation that links those three. Now the current through a component depends on its resistance. The greater the resistance, the smaller the current for a given potential difference. Now you can see that if you look at this particular equation at the top is the second one here. So you can see that if the R value were to go down, if the resistance goes down, overall in a calculation the value for I would be a lot bigger. So the current would increase, you get a greater level of flow of electricity. So let's think about types of resistors that you come across in this particular topic. One of them is the LDR. So we'll just put that in place, the LDR. Now the LDR, that stands for the light dependent resistor. And the other one that I think is worth knowing about, and is also examinable, is the thermistor. So here are two types of resistor that it's worth knowing about. Now let's talk about the LDR first. As the light intensity increases, the resistance of an LDR, a light dependent resistor, actually decreases, it goes down. So electrons or the current can flow more easily. Now light dependent resistors are often used as switches, turning on security lights when dark. So we'll just make a little note of that, just so that we've got that there. So for the LDR, that when the light intensity increases, so increase in light intensity, what we get with that is a decrease in the level of resistance that we see. Now for a thermistor, what you get is that when the temperature increases, the resistance of the thermistor actually decreases or goes down. So again, the current or the electrons can flow more easily through that resistor. And thermistors are often used as temperature sensors in car engines and in cooling systems. So once again, like the LDR with a thermistor, when there is an increase, this time instead of light but temperature, so when there's an increase in the temperature, what we get is a decrease in the level of resistance that we see. So there's two specific types of resistor that often come up in questions. So now what we're going to do is take all of this and really put it into a context when we look at our current potential difference graphs, because these are used to show how the current through a component varies with potential difference across it. And we can talk about resistance when we do this also. So let's put in three particular graphs. We're going to have one here. Let's just draw the line here. Now what we're going to say is potential difference is on the x-axis, and we're going to put current, just put a C for current at the moment, as the y-axis. And I'm going to draw the three characteristic graphs that we get. So the first one looks a bit like this. You've got a straight line directly proportional going through the origin. Now in this example what we're looking at is a resistor at constant temperature. So this first one is of a resistor at a constant temperature. So this one's number 1. Now what you get, as we said, a straight line through 0. Now the current through a resistor at constant temperature is directly proportional to the potential difference across it. So if you double the current, the potential difference would double. And this is one of the key graphs that you may be asked to draw or to simply identify in a question paper. So if the current potential difference graph looks like this, then what we're looking at is a resistor at constant temperature. Let's move to look at another example. So again, what we need is our graph in place. We'll have PD and C, so potential difference on the X and the current on the Y. Now if the graph looks a little bit like this, as you can see, it has a sort of S-shaped curve to it. This is number 2. Then what we'll be looking at is a filament lamp. So these are classic examples that often come up. So we've got a filament lamp here. Now what we get is a curved line through 0. The resistance in a filament lamp is not constant. It increases as the temperature increases. Now as more current flows, electrical energy is transferred into heat energy, making it harder for electrons or the current to flow. So let's just reiterate that again. So more current flows, you get more electrical energy transferring to heat, so the temperature rises. As the temperature rises, the resistance in the filament lamp increases. So that's why we get this kind of dip, this curve part at the top, this almost S-shaped curve. So there's our second example that it's important to be aware of. Now let's put in a third one. Third and final one. So this time we're going to have our graph again. Here, see potential difference there. So same scale. This one here is our number 3. Now this one's a bit more unusual because what we get is something that looks like this. So it's quite an unusual graph. Now this one represents what's called a diode. So this one is a diode. Now a diode has a flatter line with a very small rise. Now the current through a diode flows in one direction only. A low potential difference, as you can see, lets only a small current flow. The diode has a very high resistance in the reverse direction, so it doesn't let a lot of current flow at all, hence why we get this flat part here on the graph. So you can see there that the diode is letting current flow in only one direction. Now, an example of a diode is a light-emitting diode, an LED, and that's actually what we've got up at the top here. If I just draw a little dashed arrow to this picture at the top, this here is a picture of LED, light-emitting diodes. Now they emit light when a current flows through them in the forward direction. And there's an increasing use of LEDs for lighting as they use a much smaller current than other forms of lighting. So there we have just some key bits in this video that I wanted to talk about. on the topic of current potential difference graphs and resistance. We've linked to the equation V equals IR to potential difference current resistance, and we've manipulated that equation to be able to identify, if you wanted to, what I on its own would be and what R on its own would be. We've given two examples of resistors, the LDR and the thermistor, and said how they operate. And I've drawn the three classic current potential difference graphs that you see, the one for a resistor at constant temperature, the one for a filament lamp, and one for a diode. Okay, hope all that helps.